Hi, my name is Günzel, and today I would like to present you some recent results of our group from Design Automation for Embedded Systems under the supervision of Professor Chen at TU Dortmund. I want to talk with you about timing analysis of asynchronized distributed cause-effect chains, but to do so, I first introduce you end-to-end timing. End-to-end timing comes originally from automotive systems, where safety-critical tasks have to be completed within a certain time interval. So, for example, with an automatic brake system of a car. Typically, such behavior is not done only by one task, but we need such a sequence of tasks. And this sequence of tasks is called cause-effect chain. We look at a stream of data, which looks like this, where we have an external activity. Then the data is sampled. A chain of jobs reads and writes data from a shared resource, and with the last write event of this job chain, the data is processed and an activation based on this data can occur. Of special interest are the terms maximum reaction time and maximum data age. Maximum reaction time answers the question, how long does it take until an external activity is processed, and maximum data age answers the question, how old is the data used in actuation. So maximum reaction time is actually from here to here, and maximum data age is from here to here. In particular, we consider cause-effect chains which are spread among several ECUs. And these are typically asynchronized. So these can have clock shifts, and so the system that we then consider is locally synchronized. So on each component, they share the same clock, but globally asynchronized. The contributions of this work are as follows. So first, we provide a general but precise definition of maximum reaction time and maximum data age, which is then valid for all different task models, so periodic or sporadic, and also for different communication policies, for example, implicit communication, where we read and write the data at the start and finish of each job, or logical execution time, where the jobs read and write the data at release and deadline. Second, for the local case, we provide an exact analysis by enforcing each job of a task to have a fixed execution time. And third, we provide a global analysis using a compositional property. More specifically, we cut the cause-effect chain into local components and then use our exact local analysis on each component. This is the outline of my talk. At first, I want to talk about augmented job chains, which I use to make the general but precise definition. Then I want to present you the local and global analysis. And in the end, I want to provide an example and show the evaluation results to demonstrate the benefit of our method. I want to start by defining augmented job chains, which I use to define maximum reaction time and maximum data age. If we consider a sequence as before, and assume that the sampling happens at the first read event and the processed is the last write event of this job chain, then the sequence can be uniquely described by a tuple like this, where Z is the time of the external activity, J1 until JE is this job sequence in the middle, and Z prime is the time of the actuation. This tuple is then called an augmented job chain for the cause-effect chain E and the schedule S. In particular, we distinguish two types of augmented job chains: immediate forward augmented job chains, which define reaction time, and immediate backward augmented job chains, which define the data age. For immediate forward augmented job chains, this job sequence is defined in a forward manner. So we start with J1 and inductively define the next jobs in the sequence. The time between external activity and sampling is maximized by setting Z to the previous read event before J1, and the activation is set to the time of the process event by setting Z prime as the write event of JE. For immediate backward augmented job chains, this job sequence is defined in a backward manner. So we start with JE and define the previous job. Then Z, so the external activity is set to the time of the sampling. So that is the read event of J1. And Z, the time between processed and actuation is maximized by defining Z prime to be the subsequent write event after JE. We compute then the length of such an augmented job chain by subtracting Z from Z prime. And this defines then either the data age, either the reaction time for immediate forward augmented job chains or the data age for immediate backward augmented job chains. And the interesting part is then to compute those maximum values in the whole schedule. Now I want to show you an example how maximum reaction time is computed for a certain schedule. So we have such a schedule and assume implicit communication. So each job reads the data at its start and writes the data at its finish. Consider such a simple cause-effect chain with just two tasks. And we start with a cause-effect chain where Z is set to time 1. And to satisfy the second condition, the first job in the sequence is J12. We define then the remaining jobs in a forward manner. So J12 writes data at time 7, and this data is then used by J23, which reads the data also at time 7. So this is the second entry here. Z prime is then set to the write event of the last job, which is at time 8. And for the data stream, the length is 7. We construct the other immediate forward job chains in the same way. And then the maximum reaction time is defined as the supremum of the length of all these immediate forward augmented job chains. For the computation of maximum data age, we consider the same example as before. However, now the maximum data age, we start with the right side of the tuple. So for C5, we set Z prime to be at the 5th write event, which is here at time 13. And to satisfy the last condition, we choose J24 to be the last job in the sequence. The remaining jobs are then defined in a backward manner. So J24 reads the data at time 9, and that data was written from J12 at time 7. Z is then set to the read event of the first job in the sequence, which is at time 6. And for this data stream, the length is as well 7, from 6 to 30. In a similar way, we construct the other immediate backward augmented job chains, but the difference here is that some job chains cannot be fully constructed, as there is no previous job to be considered in the tuple. Such chains are called incomplete, and they are not considered in the computation of the maximum data age. So the maximum data age is then defined as the supremum of the length of all complete immediate backward augmented job chains. In general, the computation of maximum data age, maximum reaction time might take forever because we compute such a supremum. And to still compute the exact result in finite time, we need to utilize some task properties. So for example, if we look at only periodic tasks, then we know that the job releases repeat after one hyperperiod. This is what we prove in the paper. When we then use logical execution time, then we know that the read and write events also repeat because the read and write events are at the release and deadline of the tasks which repeat. And in this case, only finitely many augmented job chains have to be considered to compute the exact results. And this is, for example, implicitly the backbone of non-analysis like from Gordon and Chen in their recent RTAS work. If we consider implicit communication, we cannot do it that easily because the read and write events are at the start and the finish of each job, which does not necessarily repeat. And to get this, we have to fix the execution time. This can be, for example, done by spinning early completed jobs until their worst case execution time is reached. And in this case, we prove that the read and write events repeat as well. And again, only finite many augmented job chains suffice to obtain the exact results. This is what we do in our analysis. The limitation of this exact analysis is that we need to have synchronized clocks. So these, because the time has to be compared on a global level. And however, this global synchronization is often avoided because it's very much effort to ensure exact synchronization. And we have failure dependencies. So if one component fails, this may lead to a fail of the whole system then. To handle this globally asynchronized clocks, we prove some compositional property in our paper, which is here given by this cutting theory. So assume we have a cause-effect chain E, which is composed of two cause-effect chains, E1 and E2. Then the reaction time of E is actually bounded by the sum of the reaction time of the two components. The same holds for the data age. So the data age of E is upper bounded by the maximum data age of these two components. And yeah, as this is valid for all different task models, so periodic or sporadic, and all communication policies, so implicit or logical execution time or any other, and even for asynchronous tasks, which are on different ECUs, we can use this to extend any local analysis to global analysis. So we just cut it into pieces where we can then use our local analysis and get by this a global analysis. In an example, I want to show you the benefit of our analysis. So assume we have a cause-effect chain E here with 4 tasks, which is spread among 2 different ECUs. For simplicity, they look very similar here, but it doesn't really matter. The state of the art for this example is the sporadic approach by Dürr et al. And since the worst case response time is very small, the formula here simplifies to the sum of the periods, which is 6 plus 9 plus 6 plus 9, plus the worst case response time of 4 of the second task, which is 3, plus the worst case response time of the fourth task, which is 3 as well. So we get here an maximum reaction time bounded by 36. With our approach, however, we can use the cutting theory to cut the reaction time into these local components. For each local component, we can then compute the maximum reaction time by looking just at one hyper period, because as you can see, this directly repeats. And the maximum value here is obtained when we start at time 6, go 1 to the right. So this is the first job, this is then the second job, and this is from time 6 to 21, which is 15 time units. The same for the lower one. And we get here an upper bound by 30, which is already decreased by 17%. So we can see that even with such simple dependencies, our approach is already much better. For the evaluation, we use the Unifast benchmark as well as the automotive benchmark. We draw 50 tasks per task set, which are synchronous, periodic, and with implicit communication, and which have periods in the semi-harmonic set here. The utilization is uniformly drawn from 50 to 90%. And for the local cars, 2 to 15 tasks are combined per cause-effect chain. For the global cars, then 5 local cause-effect chains are combined to create a local cause-effect chain. And there is communication tasks for the CAN buses put in between. We compare with the analysis by Dürr et al. From cases 2019 and the analysis by Kloda et al. From 2018. And as the baseline, we use the analysis by Davali from 2007, which is the most pessimistic one. So these are the evaluation results for the automotive benchmark, but for the uniform benchmark, they look very similar. On the y-axis, we have the latency reduction, which says how much is our analysis tighter than the baseline by Davari. So it's basically this formula here, Davari minus the algorithm under analysis, so either Dürr, Cloda, or our analysis, divided by the latency obtained by the analysis by Davari. And for example, we can see here in the local case, the our analysis is up to 85% better than the analysis by Davari. So the maximum reaction time in the local case, the bound that we obtain is 85% smaller than the maximum reaction time bound by Davari. Yeah, we can see here for the left side, it's the local case. On the right side, there's the global case. For the local case, we behave very good already, especially for the maximum data age. We are much better here than the state of the art. And for the global case, we outperform the state of the art significantly. Our paper is as well artifact evaluated. So we have an implementation in Python 3, which can be found on GitHub. So the conclusion is that we consider in our paper these GALT systems, which are locally synchronized and globally asynchronized. We then give a precise definition of maximum data age and maximum reaction time. We provide an exact local analysis for periodic tasks by fixing the execution time of each job. We provide a cutting theorem, which can be used to extend any local analysis to a global analysis. And especially our global analysis then outperforms the state of the art significantly.